Hello everyone, welcome to my video on vector fundamental theorems. And in this video, I will show you some fundamental theorems that actually give out a vector instead of the scalar product that we're familiar with. So let's get started. So up until now, we've learned of certain theorems, such as Stoke's theorem and the Divergence theorem. And we know for each of them that if we have a simple closed domain, and of course, we're assuming that the vector field f is differentiable on every component, then we know that by these two theorems that f dot dr, where in Stoke's theorem, we know that the line integral of f dot dr over the simple closed curve C is equal to the curl of f along the surface S, where C is the boundary of that surface. And then from the divergence theorem, we know that for a simple closed surface f of f dot ds is equal to the divergence of f, where S is the boundary of the 3D region W. Alright, but one thing to note is that we know that this amount is a scalar, and same here because we know that a vector dot product another vector is also scalar. Same thing here. Scalar, scalar. However, though, so basically our the integrals that we've been seeing here all just give back a number, a scalar. However, though, what we never really considered in most multivariable calculus classes is what if we have a line integral or a surface integral, and somehow the inside here yields a vector, which implies that our result also is a vector. For example, consider f dr, where f is a scalar, but dr is a vector, so our result would have to be some vector. And same thing for here. Maybe for another example, f cross ds, where this is essentially saying that we're taking the cross product between f and the associated normal vector. And of course, this will also need to yield a vector. And so our question is well, is there any fundamental theorems that prove what this could equal to, provided that the domain is simple and closed? And so that's what today's video will discuss about in a very brief amount of time. And I would like to present the 4 equations that I discuss in my document in the blog post. And so I have that for the closed surface S, and then for the other one, it would be f cross ds, and this is equal to the negative. And of course, these two are over the closed curve C. And lastly, this one is the line integral of f cross dr. However, though, it turns out that this one is subtle and a little bit more complicated than the other 3. And it is a slightly more complicated because of the fact that when you do the derivation, you will realize that one of the integrals doesn't actually simplify very nicely. But it still has a fundamental theorem, so it's still valid. All right, so and so that's pretty much it. But I do want to show you an example of a derivation here. So for example, consider this. To find this surface integral, we usually start with the fact that ds is equal to n ds, where n is a unit vector. And we know, and then let's say that n has components n1, n2, and n3. Then we can rewrite this as fn1, fn2, where note that we are just simply multiplying f in front of the vectors. So and that makes sense because we're technically treating f as a scalar component. And we can see that we can write it as such. Now, note the fact that we can rewrite fn1, fn2, and fn3 as actually a dot product between the following. Because note that the two consecutive terms are 0. And we see that these three terms essentially just form a dot product between this special vector and n. And if you do the same, we get and thus, if we go back to our derivation here, we end up getting and you can see that if we simplify this by using the divergence theorem, because we can see that this is really just an integral, the flux integral that we're very familiar with, and because we have a simple closed surface, we are allowed to use the divergence theorem for each component. And so if I apply that, then I will get, and now notice that we have to apply the divergence of this. So the divergence of this is df dx plus 0 because the partial derivative of 0 with respect to any variable y or z is 0. And you do the same for the other two, and I will skip the explanation. And if you take the triple integral sign out and the dv's, then you end up getting But we already know what this is. This is simply just a gradient of f. And so therefore, I conclude and that ends my derivation. And you can see that this derivation exactly matches what I wrote in the very beginning. So there you go. All right, hopefully you found this interesting, since it kind of expands our scope of how we interpret vector calculus as not just some integral that always yields back numbers, but it can also yield back vectors, which increase the applicability and the usefulness in our world. All right, that's it for today. Thank you very much for listening to my videos. Please all right, guys, please like, and please subscribe. And I hope all of you will have a very nice day. All right, I'll see you guys again in the next video. Thanks.